So for this talk, I made the choice, in fact, to present science which was produced by two colleagues of our laboratory, Xiu Yin and André Berger, because it happens that in Louvain and Neuve, these are the two colleagues working most intensively on past interglacials. But obviously, I will present this from my own perspective. Well, you are all aware of the Paris Agreement, which basically urges governments to limit to take action such as to limit the increase in global average temperature by 1.5 or 2 degrees. Well, it's an interesting challenge in the sense that the target is set in terms of globally average temperature. And if scientists have recommended this choice, it's because in the context of global warming, the global average temperature is basically a summary, an indicator of the state of the climate system. So you know if you increase by 1 degree, 2 degrees, 3 degrees, you have different consequences on regional ecosystems, approach of tipping points, and so on. On the other hand, what all these colleagues working on impacts or working on policy advisors and so on, they try to get a sense of 1 degree or 2 degree means. And so for that reason, they basically tap in the pool of information provided by past climates. And that's one of the raison d'etre of the research on past interglacials. These are past warm climates. However, there is a trap, and we have a special responsibility in the way we communicate and we organize our research on past climates. And through this tool, there will be a very simple message that I hope you will all gather. And it's very elementary and simple message. So let's go through it. So the first thing, and with many colleagues and led by Eric Wolf, we recently published a review of past interglacials. And the simple message is that depending on the kind of archive you're looking at, the region you're interested in, and the climate signals you want to look at, the definition of interglacials may differ, their imprint may differ, and so consequently, you have a very different perception of what is an interglacial if you look at the Chinese monsoon compared to looking at the sea level, for example. So what Xiu, I'm sorry, I don't pronounce her name correctly, but Xiu Yin, and Chinese in the room will understand the right pronunciation. What she proposed, she worked with, well, it's a low resolution GCM. We call it an Earth model of intermediate complexity. And to give you a sense of the kind of resolution she was working with, I just reproduced this figure. So New Zealand, for example, is represented roughly by 2 grid points. But trust me, because I reproduced some of these experiments with the more, with HATSIM3, which is a more standard GCM, even though it's not state-of-the-art. And everything which we presented here actually will be valid if you work with a more complex model. And what happens is that she considered the last 800,000 years and produced a number of snapshot experiments. So when you have the last 800,000 years, you have to decide exactly which experiments you will do. And the particular strategy of that particular study was basically to focus on all the maximum in precession. And so you know that, I think for this audience, you should be familiar with the idea that the insolation, the distribution of insolation across seasons and across latitudes is controlled by precession and obliquity. And precession is controlling the maximum amount of insolation you will get on the summer solstice day. And so she made experiments of interglacials at the point of this maximum in precession. And then you ask a very simple question. Let's concentrate on the globally average temperature. All these simulations will also have different CO2. What controls the globally average temperature? And this is summarized on this diagram. It's a bar diagram. The blue is the global average temperature anomaly with respect to the average of all interglacials caused by CO2 and astronomical forcing together. The yellow bar is caused by the greenhouse gases, and the purple bar is caused by the astronomical forcing. And the message of the diagram is pretty clear. If you compare the various interglacials, the globally average temperature is controlled by CO2 mainly. But, you know, no one feels globally average temperature. You don't have a proxy for globally average temperature. You don't have a plant that respond to globally average temperature, but you have proxies for precipitation, for example, or proxies for temperature in Europe. And when you look at these more regional indicators, it happens that, for example, in this case, the annual precipitation over monsoon regions, this is controlled by the astronomical forcing. It's not a big surprise, honestly, but it reminds us that when you have, and I've seen papers that way, saying, oh, well, we should use the Holocene as an analog for a climate which is 0.5 degrees warmer than present, it's obviously completely misleading, and the same will be true for the Eemian, for stage 11, and so on. In fact, Susan compared various indicators of the climate system. For example, while the global average temperature, the temperature of the northern high latitude, and so on, there is a catalog of variables you may want to look at, and here she just summarized a few of them. And when it's mainly controlled by CO2, it's in red. When it's mainly controlled by the astronomical forcing, it's in blue. There's probably nothing very new here, but at least the study is there. And again, I show the results on monsoon precipitation, and the specialists know that Loveklim, the model used, is not necessarily the best model to look at monsoon. But with the postdoc working with me, Pablo Arayamelo, we reproduced experiments with HATSIM3, and the conclusion is exactly the same. So now you may try to have a perspective about the transient dynamics of interglacials. So you basically perform transient experiments covering several millennia, and Loveklim is perfectly appropriate to do these kind of things. So this busy diagram shows various marine isotopic stages, and I was anticipating the green wouldn't show very well, but stage 5, 9, 11, and 19, which are aligned here with respect to the evolution of CO2. And by the way, this produced more or less aligned precession cycles. So when you align the CO2, you more or less align precession as well. But you will have different evolutions of obliquity. If you do experiments with all these bells and whistles and compare the transient evolution of temperature, you have a slightly interesting behavior, which is shown here. So these are the evolutions of precession and obliquity over 3, Holocene and 2 previous marine isotopic stages commonly quoted as analogs of the present day, of the Holocene. And the various colors, I hope you can all see them, this would be the northern latitudes, the different intertropical areas, and also covering tropical areas, and now the southern latitudes. What happens when you superimpose these various evolutions, you have the impressions of phase leads and lags across the latitudes that will differ according to the interglacial you look at. The explanation is elementary. Basically, if you consider annual mean temperatures, it's mainly controlled by precession in the intertropical areas because it controls weather regimes like monsoon, and it has an effect on latent heat and then on temperature. While in the extratropical areas, this is mainly controlled by obliquity. And so depending on the alignment of obliquity and precession, you will have different apparent phase leads and lags. So that's one of the things that these transient experiments can show you. Another exercise was to estimate the length of the warm periods expressed in millennia. So in this case, the measure is the following. So Susan considered the number of thousands of years during which the temperature is higher than during the present day. And again, you will get a very different impression whether you consider the annual mean temperature or whether you consider the temperature in summer. Consider, for example, stage 19, which is usually considered as an analog for the present day, the Holocene. You will have 10,000 years during which the temperature is larger than the present day. If you consider Northern Hemisphere summer, But because CO2 was lower during stage 19, if you consider the annual mean temperature, then basically it's only warmer than the present day for 1,000 of years, and when the precession and obliquity are perfectly aligned. So I will not stop here, but I will really conclude what Hugheson's is showing, and then I will try to make a small, announcement for what is coming next. So the various messages I gave here are that the global annual mean temperature across interglacials is controlled by CO2, the globally average temperature. It's something that no one feels. There is no proxy for globally average temperature. It's a good summary to consider future climate change. It's a poor summary to consider past interglacials. So there were talks, and there is a lot of energy and time being committed, for example, to estimate the globally average temperature of the mid-Holocene. I will be slightly rude and provocative here, but basically it's a waste of time because it tells us nothing of the regional climates. So local climates are generally dominated by geological configuration, and the tricky interplay between precession and obliquity goes apparent leads and lags differing across regions. Incidentally, I didn't say that this experiment didn't consider the ice sheet. So now, why should we do research on interglacials if we are not interested on on globally average temperature? And in fact, this is all the tools which are coming now, focusing on variability, focusing on extreme events, on abrupt events. Interglacials are a pool of natural experiments, and we should basically study the conditions that are propitious to causing instability in the climate system. And I think this is really our job at this stage. We need really to focus on these aspects. Thank you very much.
I'm wondering, in this experiment, did you check the climate variability in different interglacials? So how large the different variability change with different interglacials, if you're in the transient experiment?
There is a huge echo in the room. I didn't get a word of I'm sorry, I didn't get a word of the question.
So normally, in these 8 different interglacial simulations,
yes.
So did you also check the internal climate variability, whether it changed with? Yeah.
Not here, but there is a parallel study which I did with HATSIM3, and that was the work I did with Pablo Araya-Melo, where we considered the ENSO activity, for example. And that was a poster on display on Tuesday. But just drop me an email. We have not published this work yet. ENSO, for example, is mainly controlled by the precession and level of ice, and not CO2 in that case. Even across glacial and interglacial cycles. We hope to submit that soon to Climate of the Past.
I guess you might wonder why I'm having this bowl of water here with me. It's not because I'm very thirsty, but this bowl of water can be used as a simple model of planet Earth. So in this bowl of water, we have the water, of course, and we have the air. So the water stands for the ocean, and the air is standing for the atmosphere. And the good thing is that it's a closed system. So what do we have in the atmosphere? In the atmosphere, we do have mainly nitrogen, we have oxygen, we have the greenhouse gases, and we also have noble gases. So the good thing about noble gases is that they're not involved in any biogeochemical cycles. So it means that their total amount is always the same. Another good reason why we use noble gases is that their solubility is depending on the temperature. So once we know the concentration of noble gases in the ocean, we can then derive the temperature of the ocean, and that's what we use for. So the motivation why we are interested in the temperature of the ocean is shown here. So as you all know, there's an irradiation imbalance, so there's more incoming irradiation than outgoing, and this additional heat has to be stored somewhere. Less than 10% of this additional heat is stored on land, ice, and in the atmosphere. But more than 90%, so these are the two blue curves here, so more than 90% of this additional heat is stored into the ocean. How can we measure the modern ocean temperature? Nowadays, there are more than 3,900 argofloats to measure the ocean temperature. They are able to measure the top 2,000 meters of the ocean, and if we have enough of these argofloats, we can then, in the end, derive a mean ocean temperature. But this can only be used for modern times. If we want to go back in time, we need other techniques. Another technique to have a look on past ocean temperatures are marine sediments. Thereby, the delta 18O of benthic forms is used to derive a temperature of the past of the ocean. Unfortunately, we then only get a local temperature, so we would need a lot of these benthic forms to derive a mean ocean temperature of the past. Chacun et al. Used this method that I just explained before, so they used the delta 18O signal of benthic forms to calculate a global sea surface temperature, which is shown here. So it's the red curve that is the sea surface temperature. Then here we have the dark green is the deep ocean temperature, also coming from Chacun's studies. And if we consider again the first figure, we see that the CO2, which is the yellow line, correlates quite well with the sea surface temperature. So we will now focus on interglacials, and we will consider the MIS 5.5 event, which is shown here. And our hypothesis is that the mean ocean temperature during this MIS 5.5 event was around 2 degrees warmer. So I still didn't explain how we can measure the global past mean ocean temperature. And here is now the trick that we use. So we need a device that measures an average temperature, but it also has to be something where we can look in the past. And this is done by measuring ice core samples. How does it work? As I already showed before, so by the way, that's the view from our hotel. So you can see that we have an excellent place. So the principle is quite simple. So the total amount of xenon in the atmosphere plus xenon in the ocean is constant because it's a closed system. The same is true for krypton. So that's one of these principles that we can use. And the second is that noble gases are, so the solubility of noble gases is depending on the temperature. In this figure here, you see that if we have low temperature, so if we are down here, the solubility of noble gases is high. So it means that there are a lot of xenon and krypton atoms dissolved in the water. If the temperature is higher, then we would have less xenon and krypton atoms that are dissolved in the ocean. So the only thing we need to know is the number of xenon or krypton atoms in the ocean, and we want to do it for the past. Unfortunately, it's not so easy to get this number directly, so we do it the other way around. What we do is that we subtract the number of xenon atoms that are in the atmosphere, and we subtract it from the total xenon number. And therefore, we need to have an archive of the air of the past. And here comes the ice cores into play, because the ice cores are an archive of the past atmosphere. So as I said, we are analyzing ice cores. So the ice cores are down here, and on top of the ice cores we have the firn, and here is the snow. So before the air is trapped into the ice, so before it is here, the air has to go through the firn. And if the air goes through this firn, there are some processes going on that are altering the ratio that we are considering. And the main process that we need to correct for is gravitational enrichment. This gravitational enrichment enriches the heavier species at the bottom of the fern column, so down here, and this needs to be corrected. And we are doing this by measuring the isotopic ratios of krypton and xenon. And once this is done, we will then get, in the end, a true value for the global mean ocean temperature. As I already said, we are focusing on the MIS 5, so the MIS 5.5 was the warmest period of the last interglacial. So the average temperatures of the air were around 2 degrees warmer compared to pre-industrial. The sea level was around 6 to 9 meters higher than it is nowadays. And if we consider the Arctic, there was a summer temperature on Greenland that was around 5 to 8 degrees warmer than it is now, and there's evidence that there was no Arctic summer sea ice. If we have a look on Antarctica, we also had warmer summers, so the peak Antarctic temperatures were around 4 to 6 degrees warmer than they are now, and part of the West Antarctic ice shield may have melted. And we are now interested in what's the influence on these warmer temperatures onto the ocean. Here you can see our results, but before I will discuss the results, I will shortly explain what the different curves are. So the green curve that is shown here is the delta deuterium from an EDC core. So the delta deuterium of this ice core can be used as a proxy for the local Antarctic temperature. Then we have the two blue curves, and this is the data from Chacun, who measured these benthic forms and then reconstructed a sea surface temperature, so that's this line here, and a deep ocean temperature, which is shown here. And now I will focus on our results. So we measured MIS 5.5, which is shown here, and we measured MIS 6, which is down here. And you can see that these values fit quite well with the expectations that we have. If we now focus on the MIS 5.5 only, we calculated a global mean ocean temperature, and we got a result of plus 2.3 degrees, so it means that the global ocean was around 2 degrees warmer compared to now. And this is what we actually expected, so I guess that's a success that we had. We not only measured these samples, but we also measured Taylor Glacier. And by measuring Taylor Glacier, we got a result that is quite puzzling, because only, like, if we calculate the average temperature of Taylor Glacier, we got a result that is just slightly warmer than the mean ocean temperature nowadays. And this is, of course, a big difference to these samples from the deep ice cores. First of all, we can rule out lab differences, because the measurement that we performed were also done in San Diego at the Scripps Institute, and they got the same value. So we can say that it has nothing to do with like lab problems, but it's more about the processes that are going on in the ice itself. And hereby we need to have a look at this Taylor Glacier, because Taylor Glacier ice is bubble ice. So this is ice that is brought to us by just flowing down a glacier. And if we want to get it, we just need to drill a few meters. If we then have a look at the EDC, EDML, and Vostok samples, these are all deep ice cores. So they had to drill several thousand meters to get the same ice samples from the same period. And so our hypothesis why there's such a big difference between those two ice cores, those two different ice archives, is that there was an alteration of this gas composition because this Taylor Glacier, because this Taylor Glacier ice is so close to the surface, so there may have been some alterations that influenced the ratio, or it's also possible that we did some, or that there may be some processes in the deep ice cores that we did not yet figured out that are altering the results. So to conclude, we can say that the method itself works, but there are some processes going on in the ice that we did not yet completely understand and that we will hopefully figure out pretty soon. To give a short outlook, so in the next few months we will analyze EDC samples from glacial minima and interglacial maxima to look back in time and to measure the global mean ocean temperature for the last 800,000 years, of course, not like every year, but for this glacial minima and interglacial maxima. And before I end, I want to do a short commercial. So there will be a talk by Daniel Backenstoss about noble gases during the last glacial interglacial transition, and this talk is today at 3 o'clock in the Hotel Romareda Room 2, and it's the open session on past global change. Thank you.
Thanks very much. Very nice talk. And I think it's a beautiful idea to this method that you're working on. But I'm confused about the actual results. It means you emphasize the agreement, but the temperature differences are quite distinct from the Chacun reconstruction, I think. I mean, the Chacun reconstruction looks more like I would expect, with a relatively cold Mare substage 6, and then just a little bit warmer during Mare substage 5e than today. Whereas it seems that the noble gases are showing less cooling during Mare substage 6 relative to today, and more warming. I mean, I think it was only 1.5 degrees cooler during stage 6 and 2 degrees warmer during 5e. Is that true? Could you comment on that?
So I guess it's not so easy to find a solution for this answer because so Chacun et al. Used a stack of 49 samples that were measured at, so they were only measuring local temperatures, and in the end they tried to figure out a global average temperature. So this depends very much where they measured it, and therefore it's possible that when they were measuring at cooler spots or like at spots that are less influenced, for example, by ocean circulation, that this may have an influence on the temperature. And our results are not so they give a bit, not a better, but they are more globally because they're not limited on local temperatures. So I guess that might be a reason, but maybe there are also other things that we need to consider.
Are there any other time periods where you've got a comparison between Taylor Glacier and the ice cores, so you can see whether you get a similar offset, for instance, even in the Holocene or the last glacial maximum?
Yeah, we were also measuring Taylor Glacier during the Holocene, and there we got exactly the same result. So we got just a slightly warmer global mean ocean temperature during the Holocene for our EDC samples, and we got the same result for Taylor Glacier. So therefore we are not really sure why this happens during this MIS 5.5 event.
Good morning, everyone. Thank you for being here. Thank you to the session organisers for letting me speak. And I'll take this opportunity just to acknowledge all my co-authors here. They've been a really great group of people to work with, so I've really appreciated their input in this project. So this project, I'm going to be presenting a model data comparison over the early last interglacial, and the data is stable water isotope records from East Antarctic ice cores, and the model is the isotope-enabled HADCM3. So, there's a nice introduction to the last interglacial in the previous talk, and I'm sure I don't need to spend too long on saying why we're interested in the last interglacial to the people in this room. But just to give it some context, these are three ice core stable water isotope records from East Antarctica, so deuterium and oxygen 18, spanning the last 360,000 years, with present day on the left over here. And basically what you can see is the last interglacial period stands out here between roughly 130 and 115,000 years ago, as characterized by this the significant enrichment in each of our stable water isotope records. So these kind of archives have been used to suggest a significantly warmer Antarctic climate at this time. So if zooming in now on the last interglacial, you can see a bit more that there's this distinct structure in each of the isotope records, where we have this early last interglacial peak in each of the ice core records, peaking at roughly 128,000 years ago. And then this peak is followed by a saddle-type drop or depletion in the isotope records sort of into the mid and late last interglacial. So the global context is that this period is associated with global mean temperatures somewhere between 1 and 2 degrees warmer than present. But these Antarctic isotope records have been used to infer an Antarctic climate that was more than 4 degrees warmer than present. So yeah, for this study, we take this we're interested in explaining this isotope peak that centers 128,000 years ago. So when we run our climate models for this early last interglacial period, and we just consider the orbital and greenhouse gas forcing, we find that we underestimate the proxy signal in the high southern latitudes, so we are unable to recreate the Antarctic warmth that we're inferring from the isotope data. This is based on some Betty Otto Bleisner's work with CCSM, Phil Holden with Hadsium-3, and Emma Stone compiled an ensemble of sort of last interglacial experiments and compared them to Emily's 130,000 year data time slice. So this indicates that in our models we're underestimating the proxy signal, so possibly there's deficits in the model, or maybe we're missing some feedback that we're not including in our experimental design. So looking at what this missing feedback might be, if we go back to the paleoclimate record, sea level reconstructions suggest that sea levels were 6 to 9 meters higher during this period, suggesting substantially reduced polar ice sheets. The estimate of the Greenland contribution to this sea level rise has converged towards 2 meters, suggesting that an Antarctic contribution is necessary to reconcile this sea level budget. So when we go to Antarctica, as was sort of mentioned in the previous talk, we've got this West Antarctic ice sheet, which is largely grounded below sea level on rich grey beds, and is susceptible to marine ice sheet instability. So this region has been suggested as a possible contributor to this sea level high stand. And a full collapse of the West Antarctic ice sheet would contribute somewhere between 3 and 4 meters towards sea level rise. So it could explain perhaps 50% of this reconstructed sea level. I also say, I forgot to say earlier, that the timing of this sea level peak is quite uncertain within this last interglacial period. So, but this evidence has been used to suggest that maybe a collapse of the West Antarctic ice sheet may have occurred early and may have coincided with this isotope peak. So if the West Antarctic ice sheet did collapse during the last interglacial, I guess we'd hope to see some evidence of this in the paleoclimate record. Unfortunately, Sarah Bradley has shown that there'd be very small isostatic response across East Antarctica to a collapse of the West Antarctic ice sheet. So there'd be a very small elevation signal that would be recorded in your East Antarctic ice core records. So she suggested that you wouldn't be able to tell from the elevation signal at least. However, there is some hope. So climate model simulations driven by different West Antarctic ice sheet retreat scenarios have shown that you do get warmer East Antarctic air temperatures that do extend across the East Antarctic plateau and over your East Antarctic ice core sites, and also that you would get distinct patterns in atmospheric circulation that hopefully would be imprinted on the isotope record. So these studies, again, Phil Holden, Betty, Emma Stone and Eric Steig have suggested that you could use this to kind of fingerprint or to find evidence that the West Antarctic ice sheet may have collapsed during this last interglacial period. So what did we do? We wanted to test two hypotheses for this early last interglacial isotope maximum. The first is that there was a collapse of the West Antarctic ice sheet. So for this hypothesis, we run 4 experiments with all forced with boundary conditions corresponding to 128,000 years ago, so roughly the location of this isotope peak. Our first experiment, we apply no change to the Antarctic ice sheet configuration. So this is just driven solely by your orbital and greenhouse gas parameters. A second experiment where we flatten the West Antarctic ice sheet to an elevation of 200 meters and leave it ice covered. So this is similar to the work of Phil Holden in 2010. A third experiment where we remove the West Antarctic ice sheet and replace this region with a new area of ocean, which is then able to evolve with the coupled model and grow and decay sea ice. And then there's also a fourth experiment, which is equivalent to this West Antarctic ice sheet removed scenario, but we've also included the meltwater from a collapse of the ice sheet into the Southern Ocean, which is given a isotopically depleted value roughly corresponding to the ice sheet and is distributed according to modern iceberg trajectories. And then our second hypothesis is that a major retreat of southern hemisphere sea ice could be the driver for this early last interglacial isotope maximum. And there's some evidence for this in ice core sea salt records, which are a bit qualitative but have been interpreted as representing changes in winter sea ice extent and have been used to suggest a major retreat of sea ice during this that corresponds to this isotope peak. So for this experiment, we run 2 ensembles, if you like, of experiments. The first where we use this modern West Antarctic ice sheet configuration, so no change, and then a second suite of experiments where we use this removed West Antarctic ice sheet configuration. But in these experiments, we also include a heat flux added to the underside of southern hemisphere sea ice to force different magnitudes of sea ice retreat. As you can see here. So this forcing is held constant through the annual cycle, so your sea ice is still able to grow and decay seasonally, but will just be reduced from, if you like, the couple models' equilibrium response. So this is just a list of all the experiments. So there's quite a few. So the main point to say is all our experiments are run with boundary conditions for this 128,000 year period and compared to a pre-industrial control experiment. And we also, from our sea ice retreat ensembles, we take the centre of the ensemble, just so we can maintain an assumption of linearity in our statistical model. So to our results, here we're showing the simulated isotope output between our experiments relative to the pre-industrial control. The ice core data for this 128 period is in the filled circles, and the grey line is the simulated winter sea ice extent. So our first panel is this scenario where we've applied no change to the West Antarctic ice sheet. So this is simply a response to the orbital and greenhouse gas parameters. And it's a similar story to what I suggested earlier for the temperature, that we underestimate the ice core signal. This second panel where we've flattened the West Antarctic ice sheet, and you can see there's a strong positive isotopic anomaly locally over the West Antarctic ice sheet, which is, a direct response to the surface lowering and is roughly proportional to the lapse rate, and a weak response over East Antarctica. And these 2 bottom panels are the West Antarctic ice sheet removed scenarios without the meltwater on the left and with the meltwater forcing on the right. Essentially what you can see here is none of our West Antarctic ice sheet retreat scenarios can match the ice core data at this time. So on to our second hypothesis, that a major retreat of southern hemisphere sea ice can explain the isotope data. Here we're showing each of our sea ice retreat experiments, so is along here. So plotting the percentage reduction in winter sea ice extent relative to modern along the bottom against the model data agreement. and our scenario with the West Antarctic ice sheet present on the left and without the West Antarctic ice sheet on the right. And essentially what you can see is, for both scenarios, the retreat of sea ice leads to an enrichment at each of your ice core sites. And also our best fit, if you like, our best guess of the magnitude of sea ice leads to best agreement with the ice core data is achieved at similar magnitude. So we have a 65 and a 66% retreat of winter sea ice respectively, leads to the best model data agreement. However, the credibility interval is nearly 4 times larger if we assume the West Antarctic ice sheet had already collapsed at this time. And you can see it here that basically we just can't explain the spatial pattern in the ice core data if we have the West Antarctic ice sheet removed. So this led us to conclude with a statistical model comparison that our observations are 200 times more likely if we assume the West Antarctic ice sheet was present during this period. So just quickly, spatially, what does this result look like? So this is our 65% sea ice retreat experiment, which best fits the data. As you can see, we've got good agreement with the ice core data here. And then on the right, we've got the black line is the simulated winter sea ice extent corresponding to this experiment. And for context, in blue is the 1978 to 2013 satellite data. I've not got time to go into it now, but basically our results could be evidence that for a collapse of the West Antarctic ice sheet later in the interglacial that could correspond to this saddle-type drop in the isotope records that happens after the peak. So yeah, with that I'll conclude. So a full collapse of the West Antarctic ice sheet we find can't effectively explain the spatial pattern of our ice core anomalies. And our full West Antarctic ice sheet collapse actually causes negative anomalies over East Antarctica. And this might be evidence for a later collapse of the West Antarctic ice sheet. And we find a 65% reduction in winter sea ice extent is our best explanation for the early last interglacial isotope data. And this finding demonstrates sensitivity of Antarctic sea ice to past and possibly future warming. And there's the paper for anyone who wants any more details. Thank you very much.
My question is really just about, sea ice in numerical models is notoriously fickle. How well you resolve vertical structure in the water column, just things like that. Are you concerned about that in terms of how accurate you think your result is?
I guess I'd be, so it's the mechanism we're looking at is the sea ice retreat affecting the isotope records. So it's not so much that the models, that's a problem with the models. I agree with the point that when we look at all of our models for, say, PMIP and Zembl, they all show very little sea ice retreat for the last interglacial in an unforced sense. So what we're showing is that the ice core data kind of is more consistent with this major retreat of winter sea ice extent. So as it's this additional forcing, I don't think it really, it might suggest that basically the models are too stable, if you like, maybe too tuned to present day, and the sea ice models aren't sensitive enough, or there's another forcing, such as meltwater or something that we're not including, which actually triggers this sea ice retreat. Yeah, but it'd be nice if the model would if we found some feedback that the model would internally create this sea ice retreat without us having to force it externally.
Thank you very much. Good morning, everybody. So a few people have stopped me this week and said, why are you, as a paleo sea level scientist, giving a talk on ice sheet dynamics? It's a fair question, and hopefully that will become apparent during the course of the talk. But as a consequence, I really want to acknowledge this team here, some of whom are missing off the list because we had too many authors relative to the maximum number you were allowed when you put the abstract in. And this is a group of researchers from Durham University who Erin McClaymont, who's here today, and myself pulled together with the promise of cake to have a look at this question. So this presentation is very much fueled by cake. So we're going to look at the question of, can ice sheets grow during an interglacial? And the reason for that, and the reason I got involved in this and was interested in this, is the sea level data. So Max has done a really nice job of talking about what we know about last interglacial sea levels and what the potential drivers of that might be. And as he pointed out, and this is a paper that was put together by the PALSI working group a couple of years ago in Science, the sort of best estimates of last interglacial sea level high standards in the order of about 6 to 9 meters above present. And this has been covered in a couple of the last talks. But what's interesting is the structure within that high stand. So, as has been shown now, Bob Kopp's very well used global database, I'm going to look at in a little bit more detail. So he put together in 2009 a paper that compiled a series of last interglacial sea level records, both continuous and individual data points, to come up with his... Okay? So to come up with his probabilistic assessment of global sea level. And then in a follow-on paper in 2013, he looked at the structure of that in a little bit more detail. So what can be seen is that sea level rises up through the last interglacial to the high stand at the sort of 6 to 9 meter range, and then there's a period of sea level fall. And his assessment suggests that it's extremely likely that there was at least one sizable fall within the last interglacial that's greater than 4 meters. So that's a lot of sea level. And that the sea level rise that followed the low stand, so up into here, was in the order of about 3 to 7 meters per 1,000 years. And so I spoke to Bob again, and I got him to run that analysis or double check the numbers for the rate of fall. And he thinks it's very likely within his 95% confidence limit that the rate of fall prior to the final decline from the high stand here is about 2.8 to 8.4 meters per 1,000 years. That's an awful lot of sea level. We can't look at it really at any more resolution beyond the sort of 1,000-year scale because there isn't the detail in the data. So if you take into account ocean basin geometry at this time, Pippa Whitehouse has done some estimates where she's come up with some numbers that we're looking at about 1 to 3 million cubic kilometers of ice sheet growth across Greenland and or Antarctica during that time period to be able to explain a sea level fall of that magnitude. To give you some context, the current Greenland ice sheet is estimated to be about 2.9 million cubic kilometers. So we're possibly looking to grow a whole nother Greenland ice sheet equivalent in a time where, as been shown in the previous talks, climate's warm. So that led us to this question, and fueled, as I say, by cake. Did ice sheets grow during the last interglacial? So what are the potential mechanisms for ice sheet growth? This is an area of the literature that's quite well debated, and a lot of this is hypothesized. It's quite a hard thing to be able to measure. And we summarize here in this schematic 4 potential mechanisms of ice sheet growth. So the first one, a precipitation-driven models where the side of mountain ranges is hit by prevailing winds that carry moisture would start to develop ice masses that over time, with an albedo effect and cooling, would begin to accumulate and create a larger ice sheet. The second mechanism is saddle formation. This is kind of the direct opposite of Laurent Gregoire's saddle collapse idea, where you end up with 2 ice masses within a valley-type setting, which then over time coalesce and increase in mass. The third one, less snappy title of instantaneous glaciarization of upland plateaus, takes upon the idea that if you've already got an upland area that's at the threshold of cooling and you've got precipitation in the form of snow falling on this plateau, that again you can get a feedback, a drop in the equilibrium line, and you get an increase in ice mass over time. And the final one, which we show here, is the idea of sea ice forming in a shallow marine embayment, again likely the consequence of cooling, which over time coalesces to form an ice dome. So a lot of these may interact on different timescales and at different locations. They may work together. So none of these are probably operating on their own. But these are some of the hypotheses as to how ice might develop. But can these mechanisms occur within the period of the last interglacial? So what I'm going to do is to, sort of what we did through this work was to review the literature to see whether there is any evidence for ice sheet growth in either models or proxy data. Bearing in mind the time constraints of this talk, this is a short snapshot, and I know many of you in this room have developed a number of these records. I apologize now if your favorite record is missing, but it's just to give you a bit of a summary. So here we've got a couple of model examples which typically look at the minimum extent of the Greenland ice sheet to answer the questions such as how do we contribute to that 6 to 9 metre high stand. And because of the resolution, they typically don't look for regrowth type settings. On the end, we have the new ice bridge data, which is the new radar data set, which is able to demonstrate that there was definitely some Eemian ice, particularly in the northern part of Greenland, but the challenge of flying the radar to be able to look for old ice means that we can't sort of look at this in any more detail. So if we go offshore from Greenland, what does the marine records tell us? Well, this is Anders Carlsen's paper here, and if you particularly look at this green curve, and in this case, time runs this way. We're very good at this in the interglacial community, aren't we, for not having consistent axes, but there we go. And he's used titanium here as an indicator of Greenland runoff. And as you can see, there's high levels of titanium concentration through this core, suggesting that Greenland's continuing to melt during this time. There's no noticeable drop to suggest a regrowth period. And similarly, in this now well-cited paper, which looks at pollen records off the coast of Greenland, again, evidence for the ice sheet being smaller than present, with significant amount of things such as pine growing in the area, but again, no evidence for sort of a massive regrowth of the ice sheet. So moving slightly away from Greenland, this is Henning Bau's record from the Nordic Seas, and particularly I want you to take note of this pachydermia curve here, and particularly these fall. So in this paper, Henning makes the point that potentially there is a period of cooling of a duration of about 1,000 years. We don't look at the absolute chronologies to how these tie up. You know, as Max alluded to, there is issues in timing here, so we are not trying to tie these things up. But interestingly, this is really the only sort of notable cooling period that we could find in the literature that may kind of tie in with a period of ice sheet regrowth. So moving south, just a couple of Antarctic examples. The problem in Antarctica is chronology. So there are examples of Western Antarctica being smaller than present, but which interglacial that ties to is not necessarily known. And this paper here, which looks at the biological relationships between parts of Antarctica and shows that there were seaways between some of these locations, is a really good example of this. It's a really nice case study that West Antarctic ice sheet may have been smaller, but when? And this is the challenge we have in assessing the Antarctic records, is being able to understand how that relates to our question of regrowth. And the De Conto and Pollard recent paper looks at this to an extent as well. So in black is the COP curve. This is the sea level curve that I showed at the beginning. And in blue and red are their two models that they run where they include this ice cliff collapse mechanism. And they can show an element of slowdown as a consequence of the inputs into their model, but again are unable to invoke a large sea level fall. So another recent paper, which is one of the few model papers that can kind of cause a mid-interglacial sea level fall, was this recent publication by Sutter et al. And by invoking a Southern Ocean warming of about 2 to 3 degrees above present, they were able to create a sea level low stand within the interglacial because of a feedback mechanism which then results in some ice sheet buildup. And you can kind of pick, it's a bit of a difficult graph to read on this screen, but you can pick this out in the purple line where this is rates of sea level. So we get a high rate of sea level change, it then drops again here and then increases. So there is potential for there to be a feedback mechanism which could result in some regrowth of West Antarctica during this time. It's worth just bearing in mind that in Emily's paper, the synthesis, the Southern Ocean temperature proxy data suggests a warming of about 1 to 2 degrees, and this is much kind of at the higher end of that, but bearing in mind the uncertainties, it's maybe not unfeasible. So just to move on to other locations, well, that's quite tricky, right? So we looked at Laurentide, Eurasia, Alaska, and all of them don't really provide any evidence for there being any ice in these regions. And it's quite hard to see how you could suddenly get a significant ice in these locations. So back to the questions. Well, did the ice sheets regrow during the last interglacial? Well, we think that Greenland and Antarctica are probably the only real locations where there's potential for regrowth of this size. And we see no evidence for this in the current literature. However, we are mindful that that absence of evidence may be a consequence of working in pre-LGM settings, and the evidence has been subsequently removed. But it does fit with most modelling studies, for example, this recent paper in Climate of the Past, shown on the right, that are unable to invoke large sea level oscillations due to ice sheet mass balance changes. There's one possible further component that we haven't explored, and that could be thermosteric, so the oceans responding to temperature changes in terms of its expansion and contraction. And Nick McKay in 2011 suggested that thermosteric sea level rise in response to his model of the sea surface temperatures for the last interglacial probably didn't exceed about 40 centimetres plus or minus 30. And even if you sort of take the sort of estimates of the long-term equilibrium response of about 20 centimetres to 60 centimetres per degree, you would need a global cooling of about 6 to 20 degrees in the middle of the interglacial to get a 4 metre sea level drop. And I think probably everybody in this audience would suggest that's not feasible. So, to summarise, we see no evidence for ice sheet regrowth to explain this fluctuation within the last interglacial high stand. We see no evidence for notable cooling, and also the thermosteric component is likely to be far too small. But this is really important because projections of future sea level, particularly on multi-centennial timescales, use the last interglacial as an analogue. And therefore, if we already have uncertainties as to the driving mechanisms within the last interglacial, we should be cautious in how those are applied. So my final point is a bit of a challenge to throw out to both the paleo sea level community, and Barbara raised in the PALSI session that maybe there's some uncertainties in the paleo sea level records, and also to the interglacial modelling and data community, that we really need to be able to explore not only the driving mechanisms of the high stand, but also the structure within it. Thank you very much.
Is there enough time for hydroisostatic effects to contribute to some of that?
Yeah, okay, so it's a very fair question, and I skipped over that slightly. So we did look into this, but the important thing is in the COP record, they correct for solid earth deformation. So that's already been removed from that global database. I'll put the...
Wouldn't that seem to be coupled with the fact that Antarctic and Greenland could be out of phase?
Yes, yeah, potentially. But at the current, as Max's modelling showed, there's potential that we've got melt throughout the interglacial period, and it's difficult to separate the timings of them. So yeah, the antiphase is still an explanation, but currently the data doesn't allow us to test for that. So it's a justified hypothesis.
The second largest ice sheet in the Northern Hemisphere is on Ellesmere Island. You never mentioned that. I wondered whether that grew during this interval of time. And the second point is, to what extent could large lakes in the tropics, expansion during the interglacials, have soaked up some of this water?
Yeah, okay, so we don't find any evidence outside of Greenland and Antarctica really for there being large ice caps in other locations. It's very hard to constrain because it was removed by the LGM. So I gave you a very quick snapshot of a few locations there. And from our review of the literature, and if anybody knows of anything different, I'm very happy to hear about it. We don't think there is. We have discussed the issue of potentially you ending up with mass storage within terrestrial water bodies, but from a sort of back-of-the-envelope calculation, the numbers don't add up. There would have to be a significant redistribution of water beyond the sizes of the lakes we currently see. If people have some ideas as to the fact we're well off on that, then I'd be welcome to talk about that. But currently, we don't think the numbers are right sizes.
Today, I'll give a talk about the sensitivity of the Greenland ice sheet to oceanic changes over the two last glacial cycles. And we will focus especially on the ice retreat during the last interglacial period. So first of all, the motivation of our work can be found in the recent Greenland ice sheet mass loss observed especially along the margins of the Greenland ice sheet. This fact is thought to be partly due to the intrusion of subsurface warmer waters that increase the subglacial melting below the ice shelf, leading to thinning the ice shelves and to potentially ground inline retreat. So if this kind of effect is, if the oceanic forcing is so important in the present day, it's likely that the oceanic forcing had played a very big role also in the past, when the Greenland ice sheet was bigger than nowadays and was marine-based. So to investigate how the oceanic forcing drive the retreat of the Greenland ice sheet during the Amiens, we use a new 3D hybrid thermomechanical ice sheet ice shelf model called the ELMOL that is being developed in our research group. It is based on Grizzly, and it applies the shallow ice approximation on grounded ice and the shallow shelf approximation on the ice shelves. And while on the transition zone, on the ice stream areas where the stretching and the shear regimes coexist together, we mix the velocity to ensure a smooth transition between the two regimes. So basically our model is forced by the atmosphere and by the ocean. So for the atmosphere, we calculate the atmospheric temperature and the precipitation of the past through an anomaly method in which the paleoclimatic temperature anomaly is scaled by a climatic index alpha that has been inferred from a regression of the Greenland and Antarctic signals of the last 2,050 kiloyears. So this alpha is very important in our parameterization because it ensures the evolution in time of the atmospheric temperature and the precipitation. On the other side, the oceanic changes informations are stored in the basal melting rate parameterization at the grounding line. So basically, our parameterization of the basal melting rate is linearly dependent on the oceanic temperature anomaly, as many works in literature suggest. However, here we're using a paleoclimatic temperature anomaly for the ocean that is scaled as for the atmosphere by a climatic index alpha that ensures a basal melting rate that is positive during warm periods and a negative basal melting rate during the glacials. This paleoclimatic temperature anomaly for the ocean is then amplified by a heat flux coefficient kappa that actually is our free parameter. It's which we are playing with in this work. So it's true that in the past a lot of works have been done studying the atmospheric sensitivity of the Greenland ice sheet. Actually, the oceanic sensitivity of the Greenland ice sheet has not been studied at all in the past. So there are some works in the literature that suggest that, for example, for the Antarctic ice sheet, the oceanic sensitivity should be around 10, as Renaud suggests. Anyway, for Greenland ice sheet, this parameter is free from constraint. So to study, to analyze the oceanic, to how the Greenland ice sheet reacts to the oceanic forcing in the past, we're going to play with the heat flux coefficient, launching different simulation by changing this parameter. So our results show us that the Greenland ice sheet is very sensitive to the oceanic forcing. And here you can see the evolution of the ice volume of the Greenland ice sheet along the time over the last two glacial cycles from a very low sensitivity of the ocean, the black line, to a very high oceanic sensitivity set in the simulation that corresponds to ice volume grown during the glacial of about twice the ice volume that we have nowadays in the Greenland ice sheet. So we can see that the Greenland ice sheet is very sensitive to our kappa parameter, to the oceanic sensitivity. So in this work, we're going to focus on the deglaciation through the Amiens, and we found interesting results. So if we focus on the deglaciation, on the last interglacial ice volume, we can see two interesting things. First of all, the maximum mass loss during the Amiens is higher when a high sensitivity of the ocean is set in the simulation. And on the other side, as you can see here in that graph, also the rate of mass loss is higher if a high sensitivity of the ocean is set in the simulation. So that means that when more ice is grown during the glacial, more ice is lost also during the Amiens. So both of these effects depend on kappa, on the oceanic sensitivity, although we put the same atmospheric forcing in the simulation. So which are the mechanisms that are able to explain these results? To investigate, we can consider two particular cases of the oceanic sensitivity set into the simulation. So, for example, with oceanic sensitivity that is constant in time, and it corresponds to a positive basal melting rate along all the glacial cycles. The ice volume grown during the glacial previous to the Amiens is very low. And you can see here in the glacial, in the 2D figure of the Greenland ice sheet grown during the glacial, with this particular oceanic sensitivity, the ice sheet is land-based, so it's not able to expand through the continental shelf. And also, if we look at the rate of mass loss, we can see that for the whole deglaciation, the rate of mass loss in terms of sea level equivalent is about 2 meters along across the whole deglaciation. So, on the other hand, if we consider a very high oceanic sensitivity in the simulation, we can see that the Greenland ice sheet starts to react. So the ice grown during the glacial is very high, it's higher than before. The ice sheet is marine-based, and it was able to expand throughout the continental shelf. And also the rate of mass loss is equivalent during the whole deglaciation is equivalent to 7 meters in sea level equivalent. This is about the amount of ice that we got nowadays in the Greenland ice sheet. So it's a very big rate of mass loss. So summarizing these very interesting results, we can explain why if more ice is grown during the glacial, more ice was also lost during the Amiens. So if we focus, for example, for the high oceanic sensitivity case, we saw that the configuration of the Greenland ice sheet during the glacial is like this. So the ice has grown through covering all the continental shelf, and the whole Greenland ice sheet is marine-based, so much more exposed to the oceanic changes of the past, and so its submarine melt is able to easily trigger the ice retreat. So thanks to the great basal melting rate at the base of the ice shelves, Greenland ice sheet starts to lose ice at its margins, and this ice loss makes the thinning of the ice shelves and leads to granular retreat. So this effect actually is not only locally confined, because it's able to propagate inland, causing an increasing of the advection of ice from the interiors of the Greenland ice sheet. So the ice thickness decreases and an elevation melt feedback begins. So with these mechanisms, we are able actually to justify the increasing mass loss rate for high oceanic sensitivity. Anyway, to explain also why more ice is lost during the Amiens for a hygroceanic sensitivity case, we have to introduce also the isostatic adjustment effect. Actually, during the glacial, when we have a hygroceanic sensitivity, thick ice is able to cover regions that were previously ice-free. So thanks to the elastic lithosphere and to the pressure of the ice, the bedrock sinks of hundreds of meters. So during the interglacial, the slow isostatic rebound makes the basal melt more effective as the ice retreats inland. And that effect, combined with the basal melting rate that is high during the interglacial, lead to more volume loss and more rapid retreat. So they both work together in a positive feedback. So to summarize our results, we can say that the paleoceanic sensitivity of the Greenland ice sheet is investigated for the first time as an active forcing. So if we want to correctly model the evolution of the Greenland ice sheet in the past, we have to consider the ocean as an active forcing. That because the oceanic forcing, as we saw, plays a crucial role in the evolution of the Greenland ice sheet through the cycles driving, for example, in cold periods, the ice advance for refreezing, and during warm periods, driving the retreat of ice, thanks to the submarine melting. So, we also saw that both submarine melt and isostatic adjustment drive the ice retreat from the continental shelf in a positive feedback. So, and especially the rate of mass loss is due almost completely to the submarine melting during the interglacial, while the maximum ice loss that is higher for a high oceanic sensitivity is due to a positive feedback of the two components of our driving. So, thank you.
At the end of your talk, you said that you can also compute the isostatic rebound due to your ice sheet evolution. So the isostatic rebound is not an input in your model, it is computed. So if it is so, you can also compare your findings in terms of calculation of the isostatic rebound to measurements, and I would like to know if you can do that and if you have done it.
Mm-hmm. Yes, actually, it's computed as a isostatic rebound, and we set a time of rebound of 3,000 years. That is normal use in the simulations. So, but of course, it will be interesting to analyze other time scales of the rebound to see actually how this effect is able to drive the retreat of ice.
There was a lot of discussion about which of the past interglacial may be the most suited for understanding the natural variability in a warming world. I'm very pleased to have heard so many arguments this morning of continuing to study the last interglacial, although this might not necessarily be the most suited for that. Today I'd like to present you a new speleothem record from the Northern Alps, and I hope with this to contribute on our side to understand what is the regional adaptation of a warming climate. So just to make things clear, when talking about the last interglacial, I'm referring to this period between 130 and 116 kiloyears before present, which has been observed in the marine sediments with a delta O18 depletion and has been described in continental records by mainly pollen data in northwestern Europe as the Amiens, or in the Alps as in the older alpine literature as the Northwest Interglacial. It is also known for a while now that there might be a lag between the continental response and the marine response. So we have seen these plots already this morning. On a global scale, we had a higher sea level of about 6 to 9 meters. In Western Europe, this climate was expressed by a rather more humid and warmer environment. In a very recent study, Attila Demeni and co-authors have tried to compile the existing high-resolution stable isotope records across Europe based on speleothem data. And these authors concluded that there was a general trend towards more positive delta 18 values along the interglacial. Combining their data with delta C13 values, they concluded that there must have been a climate optimum between 124 and 120,000 years ago. Now, if we look a bit in more detail in these records, we see actually quite a contrasted response. For instance, on this upper panel with the Corchia speleothem record from northwestern Italy, which responds mainly to an amount effect, as compared to the recently published speleothem records from the Northern Alps, which are interpreted as responding to a temperature record. So this leaves us with the question whether there was indeed a climate optimum in Western Europe between 124 and 120,000 before present, and eventually how this signal connects on a larger hemispheric scale. So to try to contribute to these questions, we are going back to the Siebenhengste karst system located in central Switzerland. This is a high-altitude karst system between 1,700 and 2,000 meters above sea level. Present-day precipitation is above 1,500 millimeters a year, and the mean annual temperature is 2 to 4 degrees. There are more than 30 known cave entrances in this carbonate outcrop here at the back, which lead to the second largest cave system in Western Europe with over 150 kilometers of connected cave passages. A study published 2 years ago has revealed that the moisture advected to this cave site is mainly sourced in the northeastern Atlantic, although there might be some natural reconvection during the summer season in this area. So far, we have no reason to doubt that this a similar pattern happened also during last interglacial. So we went into this cave and sampled a speleothem from this location here, pretty close to the surface, some 50 meters below, about in the same area than a recently published LGM speleothem, which is located much further down. The sample was found broken on a cave passage and grew more or less between 133 and 83,000 years before present, although there are some hyati in the top part of this sample. Today, I'd like to focus on this part here, which is characterized by a very distinct fabric with brownish colors, and has been deposited between 130 and 118,000 years before present. So, looking at this record, we notice straight on that there are two different modes of deposition. On the first hand, we have in the early section of this stalagmite, between 134 and 130,000, very fast-growing speleothem deposition, which is combined with very depleted delta 18 values and extremely high delta C13 values. We associate this signature to a still ice-covered catchment during stadial 6. During stadial 5, we observe a much slower growing stalagmite, which is characterized by a delta 18 value peaking around 129,000 years before present, and much more depleted delta 13 values. Although this does still not reflect a proper soil cover, there might be an indication that there is kind of lag between the delta 18 record and the most depleted delta C13 values. We also noticed that this speleothem, or this growth phase, stopped around 117,000 years before present, which is concordant with the onset of Greenland stadial 26. So when trying to compare our record now with the existing knowledge about the Siebenhengste data, we may try a comparison with the LGM samples deposited around 25,000 years ago. We have a total amplitude which reaches 4 to 5 per mil, and although this is a very rough approximation, and I'm still very cautious about that, this would correspond, assuming a temperature dependency of 0.33 per mil per degree, to a total temperature amplitude of 12 to 15 degrees. When comparing this with the present-day precipitating calcite, we have again an offset of about 1 per mil, which here corresponds to about 3 degrees warmer than present days. We gain confidence in this record when comparing this with the published Greenland synthetic record, which has been modeled based on a seesaw pattern. Actually, we observe quite a good match between these data, and this allows us now to push on the comparison with more regional records. Our speleothem data, shown here on the top with the red curve, corresponds pretty well to what has been observed in Korkia Cave, or considering an inverse delta weighting scale. However, there are also some marked differences with the previously published alpine dataset from the Northern Alps, where we see during that time period a clearly marked negative excursion in the delta weighting. Although the interpretation is not very detailed so far, we attribute this difference mainly to the altitude difference between these cave sites, where this period may have been associated with enhanced evapotranspiration in the area, which possibly influenced the hydrological recharge. So, we are trying just to compare this data now on a more hemispheric scale, and when it might be a bit a strange comparison, but actually when we try to compare the Siebenhengster record with what we know from Eastern Asia, we see no proper correlation between these two patterns. This is not necessarily unanticipated, but it very much in contrast to what we observed during the LGM in the same cave, where we have actually quite a nice match between the Siebenhengster delta weighting record and the Eastern Asian delta weighting record. Overall, we suggest that this fits with our conceptual understanding of this period where we had a southward shift of the westerlies, isolating a bit more the Greenland ice sheet from the Western European signal. This will have to be investigated, obviously, in far more detail than what I can present today. Anyway, if I want to take some conclusions of this new record, is that we see quite a good correlation with Greenland during interglacials, that the end of termination 2 has been dated to 129.6 plus minus 0.6 kiloyears. The full interglacial conditions are reached around 128,000 years before present, and that this would correspond to a roughly 12 to 15 degree higher temperature than what was observed during the LGM, or about 3 degrees warmer than what we observe today. This comes to a temperature at 1700 meters above sea level in Central Europe of about 6.5 degrees. And the sample stopped growing at the onset of Greenland Sail 26. Thank you very much.
Well, we will keep talking about continental carbonates, but let's get out of caves and go to open air conditions. Talking about calcareous tufa, which precipitate from spring and river water. The request weight and temperature conditions, so they are mainly depositing during interglacials, at least in European area. And what is very important is that they are mainly in large valleys, full interglacial conditions are only recorded in calcareous tufa at the top of terrace sequences. Tufas are very, very good to preserve in situ paleontological data, which allow paleoenvironmental reconstruction. They mostly record mollusk shells that are very good paleoenvironmental proxies. And as they precipitate at ambient temperature, they are suitable for the use of isotopes for climatic reconstruction. I will make it short, but in calcareous tufa, the data 18 is mainly depending on mean annual temperature, air temperature, when you're walking at a single site, but at the European scale, you can see some variation depending on geographical parameters as well as air mass and sources and composition. Data C13 depends on the relative contribution of different carbon sources to the dissolved inorganic carbon of water from which tufa is precipitating. And the two main sources are vegetation and soils that are well developed during wet periods, and the aquifer, the limestone composing the aquifer, and during wet period exchange between limestone of the aquifer and groundwater are reduced because residence time is reduced. So basically, delta C13 is more negative during wetter periods. The Holocene is quite well represented in European tuffers because of preservation, of course, but also because they have been widely studied since basically the 80s. And they already provide an extended isotopic data set of oxygen and carbon. But we may notice that there's an over-representation of early to middle Holocene sites, probably because something happened during the late Holocene, called the late Holocene tuffer decline, and so there are fewer sites for the second half of the Holocene. Anyway, when comparing data from different European sites, be careful here, the scales are reversed. So comparing data from different European sites, you can see that geographical parameters clearly affect the isotopic signal, mainly continentality from west to east, and some effects of the aridity from north to south. Regarding Pleistocene interglacial in European tuffers, the best represented interglacials are MIS 5 and MIS 11, which suggests that conditions were probably more suitable during this period than during other Pleistocene interglacials. Probably one possibility is a temperature effect, or although the timing and duration of the interglacial, how quickly the warming happened at the beginning, but those possibilities, I'm not confident about those because you can see that at the beginning of the Holocene, a lot of tufa already precipitated, even before, well, even earlier. And the stronger parameter is probably humidity, because you can't have tufa if there is no water. That's a very basic parameter. And just to illustrate, you can see here in this Holocene tufa from Slovakia that the tufa precipitation rate is clearly increasing when springs are more active, which can be shown by spring mollusk development. That means that the occurrence of tufa itself suggests that conditions were wet during MIS 5 and MIS 11. So we will focus on these two interglacials. So compared to the Holocene record, Aeolian tufas are less preserved and studied in Europe, but there's still a growing isotopic data set from various sites across Europe. And if you put here in yellow data from the Aeolian compared to data from the Holocene, we already see that continentality and aridity effects could be similar to the Holocene, but this data set is too weak to have strong conclusion. And for the MIS 11, there's some sites as well, but they have been poorly studied, and only one site in northern France has provided a continuous isotopic record in oxygen and carbon. So we will focus on northern France and the Paris basin because they are very interesting sites from a similar geological context, mainly limestone and chalk from the Paris basin, and they are nowadays under similar climatic conditions, mostly temperate oceanic. And those three sites that I will present to you briefly afterwards are very well dated and provide very good paleoenvironmental and paleoclimate reconstruction. Saint-Germain-le-Vasson is well assigned to the first half of the Holocene. He provides a very good malacological and some palynological data. And he has isotopic distribution similar to other sites from England, northern France, and Luxembourg, and the shape of the radiations are similar to other Holocene sites. So this could be a reference for northern France. Cahors is a very, very interesting site for archaeology, but also for reconstruction of paleoenvironment of the MIS-5E, of the Aegean. During the optimum, during the main archaeological level, the optimum is well recorded by isotopic record, but as well by mollusks and large mammal faunas. And finally, Lassell, which is very well assigned to MIS-11 interglacial, with a nice optimum, very well recorded by mollusk biodiversity, which is very, very high, and development of forest biotopes, but also the occurrence of different 1,000 taxa. And this optimum is well recorded in geochemical data as well, with warm and humid conditions recorded. I just want to notice this last period at Lassell, which record very wet conditions during a cooler period. And why did I show you that? It's because when comparing all data from all three sites, you can see that they have consistent ranges and means, except those data that correspond to this wet and cooler events at Lassell. In details, comparing MIS-11 and the Holocene, so Saint-Germain-le-Vasson and Lassell, you can see that except from this very humid episode during MIS-11, this older interglacial is definitely wetter than the Holocene and slightly warmer. And we can also compare the optima of each interglacial. Those optima has been defined on paleoenvironmental data, not only on isotopic data. And you can see that the MIS-11 optimum was definitely warmer and wetter than the Atlantic optimum in northern France. And we can do the same for MIS-5E and the Holocene. And in this case, you see that the Aegean show similar temperature than the first half of the Holocene. But humidity is quite different. The amplitude is definitely narrower, which means that the Aegean was as wet as the wettest conditions recorded during the Holocene at Saint-Germain-le-Vasson. Regarding the optima, the Aegean optimum is clearly wetter than the Atlantic, but there is no significant differences in temperature. So just to conclude, so here I synthesize what I've just told, but I want to insist that in northern France, the Pleistocene optima seems definitely warmer and wetter than the Holocene, and that MIS-11 appears definitely warmer, the warmest, which is consistent with the paleoenvironmental data I've shown you, and especially the presence of southern taxa that are not existing anymore in the Seine Valley in northern France, and especially macaca, which need very warm conditions during the whole year, and it can't survive a cold winter. And this is only preliminary results. We definitely need to extend the data set to other European areas. And I would like to build a database to better compare those interglacials in Europe, to keep doing this kind of diachronous comparison, but also to compare the European variability of those interglacials with this kind of diagram, but also using isotopic maps built through a GIS linked to the database. Thank you for your attention.
How do you get the absolute dating for Miss 5 and Miss 11?
Yeah, there's several datings from different methods on the tufa itself by uranium thorium, but also on the archaeological material, on bones, and on the sands below the tufa.
So hi everybody. So today I will be talking about the climate dynamic of the termination 2 and 3 in East Antarctica as inferred from the combination of water and air isotopes in Dome Sea and Vostok ice cores. So first the study area. So I work on the Vostok, it's the Russian base, and the ice core cover 400,000 years, and the Franco-Italian base, Dome Sea, and the ice core cover 800,000 years. So the both sides are extremes. It means very low temperature and very low accumulation, like you can see. So the informations trapped in ice cores. Here is the Vostok ice core, and in blue is the CO2. In red is the temperature reconstruction, and in green is the methane. And you can see the succession of glacial and interglacial periods, so termination 1, 2, 3, and 4. And the most important is to understand the phasing between the increases in temperature and greenhouse gases concentration during the large climatic transition. But we have uncertainties on the quantitative estimates of climatic parameters, and especially for glacial periods, because we don't have any present-day equivalent to Vostok and Dome Sea ice cores. So we can use water isotopes, the delta O18 and the delta D, is the deuterium, for reconstruct the past temperatures and the past accumulation. But for the past temperature, it's just empirical basis, and it's based on what we observe today. So along the trajectory of the water cycle, the water isotopes record all the information about the temperature and the precipitation, and at the end of the trajectory on the water cycle, it's trapped in ice. And we can use only air isotopes, delta N15 and delta argon-14. So they are trapped in a bubble in ice core. During the transformation on snow into ice, it depends on temperature and precipitation condition, and it occurs in a few decades to several millennia. For Dome Sea and Vostok, it's more than several millennia. And the bubbles are completely closed around 60 or 100 meters depth. So for this, the ice is always older than the entrapped gases, and this is delta H, but for this study it's not very important. But what is important is the thermal fractionation and the gravitational fractionation. If we look the delta N15 and the delta argon-14 is different for the thermal fractionation, so we can see if we make the difference between the two proxies if we have a thermal fractionation in this ice core. And for the gravitational fractionation, it's the same for the both proxies. So the air isotopes give us information on the past fan thickness. So just for summarize, we have 4 proxies, 2 water isotopes. They give us information on past temperature, past accumulation, but it's not perfect. It's empirical, and we have to extrapolate for the glacial periods. And we have 2 air isotopes. They give us information on pan phase thickness, and then depends on the past temperature and accumulation rate, so they give us information on these 2. But we have a mismatch between measurements and simulations during glacial periods. If we look at the delta N15, for example, if the accumulation increases, the delta N15 increases too, and if temperature decreases, the delta N15 decreases too. And if impurity content increases, we don't know. So the idea is to combine these proxies to progress in the quantification of the climatic parameters. So the results. Here we have the air and water and air isotopes of termination 2 and termination 3 for Vostok and Dome Sea. So now, until the end of my presentation, in green it's for Dome Sea high score, and in purple it's for Vostok high score. So we can see here is the delta D, the deuterium. We have a very similar amplitude and very similar profile for the both sites. But if we look at the delta N15 and the delta 40 argon, we have a very different signal in delta N15, especially in the termination 3. We have a strong increase for Dempsey in green, and we have a small increase for Vostok, and we don't know why we have this difference. So we look different climatic parameters, the impurity, the temperature, and the accumulation to understand which parameter influence this gap and this difference between the two sites. So first, the impurity effect. So here we have the concentration of calcium, and we can see they are very similar for the both sites. Just the exception is for the peak before the termination 3, and if we look, is not synchronous with the increase of the delta N15. So we are sure that the concentration of calcium don't influence the delta N15. So it's not that. So we look at the temperature. So here we have the temperature gradient is the temperature calculated with the model densification with heat transfer, and is the difference of temperature between the top and the bottom of the firm. It's just to compare with these amplitudes. So here in light and dark green is for Dempsey, when it's T site is the reconstruction of temperature with the isotope, but with the correction of the delta O18 to the ocean and the DXS. And when it's just isotope paleothermometer, it's just the delta O18. So we can see we have a very similar profile. We have difference with amplitude, but the profile are very close. So the temperature effect maybe can explain the part of the discrepancy, but if we look here, we can reconstruct the thermal fractionation because we have delta N15 and delta argon 14 for the termination 2 in Vostok, and we don't see a thermal fractionation, so maybe it's just not observed, and maybe it's not just the temperature. So we look the accumulation effect. So here I make a zoom in termination 2, so we can see it's the same like before for temperature. We have two reconstruction with only isotopes, and with the isotopes, but constrained with the modelizations. So ICC 2012. And here we have the difference between the two sites, but it's the same amplitude. But if we look at the termination 3, here we have a difference for the reconstruction of the accumulation rate between just the use of isotopes and the use of dating constraints. And we are looking with this gap with 1 centimeter, what equivalent in the increase of delta N15. So if we look at this graph, is the modelization of delta N15, and if the accumulation increases to 1 centimeter, the delta N15 increases to 0.1 per mil. So if we look the water and air, the air isotopes, we can see the difference for termination 3 between Vostok and Dempsey. It's around 0.09 per mil. So the accumulation effect can explain most of the discrepancy. And the last question, and it's very the beginning of the study, so I don't have the answer, is how explaining the different timing for delta O18 and delta N15 increases at the onset of the termination 3. Is this here in around 260,000 here? I have the start of the increases of the delta N15, and it's not at exactly at the same time for Vostok, but we have the increase here. But if we look the deuterium, the water isotope, we don't have. It's very stable. And if we look the delta O18 planktonic, we see this increase, but it's not very at the same time. So maybe the water isotope miss a climatic signal. So to conclude, the water isotopes permit to reconstruct past temperatures and accumulation rates. The air isotopes give us the past strand thickness and inform us on the evolution of temperature and accumulation rates during climatic transition. The impurities cannot explain the difference between Dempsey and Vostok during the termination. The temperature changes can explain a part of this difference, but not all the amplitude. And the accumulation changes can explain most of the discrepancy. So the combination of water and air isotopes can improve the quantification of climatic parameters in the past, and especially during glacial period when we don't have a present-day equivalent. So thank you for your attention.
You see this discrepancy, you said, between delta 15N and delta 018 or deuterium. Could it be linked to an issue with the delta H at that time period? Could the discrepancy you see between air isotopes and water isotope be just linked to a problem with the H scale and the delta H estimate?
Yeah, I am thinking about that, but no, because we have made the synchronous with the typons, and it's not that. So yeah, it was an idea, but yeah, I don't think so.
We could see very different evolution during the last interglacial between Vostok and Dome C. Is it only linked to the different resolution, or do you think something else happens?
Maybe for the resolution, that I don't know for the Vostok ISO because it's Russian based, so I don't have access of all the data. But I'm not sure if the discrepancy come from the resolution of the measurement, but yeah, maybe it's a good idea, maybe.